The goal of this lab was to observe the motion of a mass on a spring that swings in an arc while simultaneously oscillating. This motion was observed in two ways: experimentally using video analysis with tracker software, and predictively using a Python computer model. The system's motion was analyzed with Newton's second law, while the system's energy changes were analyzed with the energy principle. Ultimately, I found that motion data between the experimental and predictive data differed. The actual mass on a spring that was analyzed with the tracker fell farther than the computer model predicted, but it also did not rebound quite as high. As for the energy changes of the system, potential and kinetic energy changes were periodic, but total energy remained the same. As stated in the introduction, Newton's second law was used to analyze motion. When analyzing motion, the system in consideration was just the mass that was attached to the spring. The energy principle was used to observe changes in energy. In this case, the system in consideration was the mass plus the spring and the Earth. Here's my analysis of the video's system motion using tracker. Note that the mass of the object on the end of the spring was 0.402 kilograms. The origin of my coordinate system is the point at which the other end of the spring is attached to a rod. Here are the points of the mass's motion, as well as a plot of y position versus time. Next, I will show the setup and results of my Python program. Here is some initialization code. Mass was given, initial position and velocity were derived from tracker data. Here are the values I calculated for spring stiffness and the relaxed length of the spring. Here's how the spring constant was calculated. We know the formula for the time period of oscillation. This can be rearranged to isolate the spring constant. A value of t was determined from the tracker data, and we have all the other necessary information to solve for the stiffness, which is 6.878 newtons per meter. Here's how the spring's relaxed length was found. We know that the magnitude of the gravitational force on the mass is equal to that of the spring force. Values that constitute these forces can be rearranged to isolate the L0 variable. This too can be solved for with data we are given, as well as the stiffness value we just calculated. The spring's relaxed length is calculated to be 0.127 meters. The three system energies at play here, kinetic, gravitational potential, and spring potential, are introduced here with the formula for each. The calculation loop begins here. The two forces, gravity and spring, are computed with these lines and added here to find net force. This net force is plugged into Newton's second law to update the velocity and position of the object. Next, the spring force is updated according to the object's position and the stretch of the spring. Finally, energy changes are found in the calculation loop using the object's position and formulas for each type of energy involved. Note the code calculates energy change, not just energy. This is consistent with the energy principle. Total energy change is equal to total work that is done to the system. Here is the computer model's visualization of the system's motion. This is a plot of the motion of the object in the experiment, in red, and the model, in blue, over time. Notice the discrepancies at the peaks and troughs of the curves. Why do these discrepancies exist? It could be due to dissipation due to drag force that takes place in the experiment. No drag force is present in the computer model, which is a completely closed system. Also, these differences may be because the initial conditions I established in my code were inaccurate. If the initial position of the ball was even slightly off, it could have had a drastic impact on the motion data produced by my code. Here's a plot of energy change versus time. Notice that although the changes of all energies oscillate, the total change in energy at each point in the plot is zero. Do these findings satisfy the energy principle? Absolutely. The energy principle posits that the total change in energy is equal to the total change in each energy present in the system. Because no work is done on this system, total energy change should be zero, and according to my data, the system energy does not change at all over the course of the experiment. The period of oscillation in the x direction of the experimental motion was 1.615 seconds. This was calculated by finding the time it took for the object to return to its peak x position once. The x period is dependent on the force of gravity that swings the object from side to side. The y period was calculated in the same way and was found to be 1.519 seconds. Unlike the x period, it depends on the spring's stiffness. Because the periods in the x and y directions are dependent on different factors, it makes sense that they are slightly different. Also, the object moves horizontally in an ellipse, but up and down vertically. So it makes sense that it takes longer for it to complete a period of motion in the x direction.